Ladies and gentlemen, Brian Goetz.
Hello, JFocus. So this is actually my first time at JFocus. I want to thank Matthias for inviting me to come do the opening keynote this year. When he was discussing this with me, he told me about how wonderful the weather was in Stockholm in February. So with a sales pitch like that, you knew I couldn't refuse, right? So my talk today is entitled Move Deliberately and Don't Break Anything. This is a little bit more of a philosophical talk, a little bit less of a technical talk than I usually do. And it is about how we approach evolving the Java platform, where we've been, where we're going, and how we think about it. So hope you enjoy it. All right, let's get set up here. We good? We're good. All right. So what I'm going to talk about today is about time, and in particular, our perception of time as software engineers. The time scale in which our products live is different from a lot of industries, and it affects the way we work. So as software engineers, I think we kind of have a bit of a distorted sense of time. In a lot of companies, the highest technical title is architect, and architect is a role that's been around for many thousands of years. Now, in theory, software should last longer than buildings or bridges because software isn't subject to the whims of uncooperative weather or geology. But in conventional architecture, making buildings that could stand for 1,000 years is something that we knew how to do, well, almost 1,000 years ago. In software engineering, even 5 years can seem like a long time. And a lot of the focus of what we do is aimed at building things for right now, not for next year or 5 years from now, or certainly not 1,000 years from now. But systems also often live longer than we expect them to. And in successful systems, we spend a lot of our time adapting the systems to meet new challenges. Now, the system I work on, the Java platform, is old by comparison to most of the systems that people in the audience here work on. This year, Java is 20 years old. That's pretty amazing. And for the last 5 years, I've had the immense privilege of piloting the evolution of the Java language. And so I'm going to share some of my thoughts about the challenges of evolving a mature platform, and one that has millions of users who notice when you change anything. A few lessons I've learned along the way, and some thoughts about where we're going next. Because we are looking ahead, and we want to ensure that Java remains vibrant for at least the next 20 years, probably not the next 1,000 years. So the title of this talk refers to a quote from Facebook CEO Mark Zuckerberg from a while back, which was, "Move fast and break things." Zuckerberg advanced this as a motto for the Facebook engineering culture in the early days. Telling the team it was more important to make progress on improving the user experience than to worry about preserving what was already there. And this may have started at Facebook, or at least been popularized at Facebook, but it certainly didn't stop there. And not only is this part of the culture of most startups, if you listen carefully, you'll hear some developers implicitly assume that this is just a basic fact of software development in general. Now, it's not surprising that engineers are drawn to a catchphrase like this. After all, breaking things can be fun. And certainly breaking things is easier than improving them without breaking them. And the parts that slow you down in your job are often the boring and unglamorous parts. So who wouldn't want permission to ignore all of these things? But it's really easy to take this too far, and some people certainly do. It's even possible to start thinking that if you think progress requires breaking things, you might even confuse breaking things with progress. And of course, what Zuckerberg meant was not about breaking things, it was about building things, because breaking things really isn't a good thing on its own. And in fact, usually breaking things comes with legal and financial consequences. So the intent of saying move fast and break things is not to endorse vandalism or to celebrate destruction. It's to create the opportunity to build something even better than what we have now, without being slowed down by the need to preserve the status quo. In other words, giving people permission to value what could be over what is. And giving permission to break things so that better things could be built in their place is not really expressing a technological or a social viewpoint as much as an economic one. Zuckerberg was, knowingly or maybe not knowingly, appealing to the work of the economist Joseph Schumpeter, who coined the phrase creative destruction to describe the inevitable fact of capitalism, that progress comes at the expense of what came before. The growth of new industries inevitably brings around the decline of old ones. So it's notable that Facebook doesn't say this anymore. Last year, Zuckerberg retired the old motto and brought out a much less catchy one in its place. So what he's saying is, sure, progress is still important, but not at the cost of destabilizing the user experience. So what changed? Well, when you're a startup with no users and a bare bones product, the economics all point you towards making a lot of progress really fast, regardless of the collateral damage or the accumulation of technical debt. Because if you don't make some progress fast, you're going to run out of money. You're going to get scooped by the competition. You'll be out of business. On the other hand, if you're the market leader, you have a mature product, the economics all point in the other direction. You don't have as far up to go, and you have a lot farther down to fall. So it's not surprising that startups are more concerned with progress while more established businesses are concerned with stability. In fact, the singer Bob Dylan said it pretty well. When you ain't got nothing, you got nothing to lose. So move fast and break things is a really sensible strategy when you're a plucky startup, hoping to rise above the crowd and get some attention and get your name known, and a lot less of appropriate a strategy when you have 1 billion users. So the point of this is, the priority balance between progress and preservation isn't a technical decision, it isn't a social decision, it isn't a cultural decision, it's an economic decision, it's a business decision. Move fast and break things isn't a philosophy. It's not a strategy, it's a tactic. And hopefully it's a tactic that's employed in the context of a sensible cost-benefit analysis. So one thing that separates the grown-ups from the kids, I think, is the understanding that programming is fundamentally an economic activity. Technology is exciting and fun. I love programming. I've been programming for 35 years, and I hope to continue doing it for another 35. And I feel incredibly lucky that I get to do this for a living. But programming is a means to the end. It's not the end in itself. If it were cheaper or faster to build Facebook out of rubber bands and duct tape, then with PHP, that's what they would have done. And I guess some people, I know what you're all thinking, right? You're thinking PHP is rubber bands and duct tape, and that's an interesting conversation, but that's a different talk. But like any other economic activity, we can measure, or at least try to measure, the inputs and the outputs, and ask ourselves, whether we're getting a good return on our investment. So the inputs to programming are pretty simple. You've got developer time and pizza, basically, right? Those are the inputs. And the outputs are a little bit harder to measure, but we hope in any successful scenario we're going to get some amount of working code, and we're probably also going to accrue some technical debt. And you can think of technical debt as the obligation to provide more developer time and more pizza later in the future, assuming you stay in business. So moving fast and breaking things is a conscious choice to say, I want more of both of these outputs, more working code and more technical debt for a given amount of pizza, right? This is a simple economic decision. And in some cases, when you've got nothing to lose and your investors are breathing down your neck, this can be a perfectly smart business choice. But remember, this is a business decision based on business considerations, which change over time. It's not a philosophy. By moving fast and breaking things, you're choosing to value time to market over stability and future maintenance costs. So to bring this point home, I pulled out some quotes here from a really nice article by Jocelyn Goldfein called "The Right Way to Ship Software." And I'll give you the secret ahead of time. There's no right way to ship software. It all depends on the business context, of course. But what Goldfein had to say was, in a profession where we carry out decade-spanning holy wars over tab widths and capitalization, it's not any surprise that people get attached to their development and release habits. But if shipping so much software has taught me one thing, it's to be agnostic. Different methodologies optimize for different goals, and all of them have downsides. If you maximize for schedule predictability, you're going to lose out on engineering productivity. And this all leads up to a sort of desperate plea to developers. My fellow engineers, please stop asking, is this process good or bad? And start asking, is it well suited to my situation? Now, Goldfine was, knowingly or not, appealing to the philosophy of Charles Saunders Peirce, sometimes called the father of pragmatism, who in 1878 framed what is now called the pragmatic maxim. And it's a little bit wordy, so I'll summarize what Peirce was saying. Pragmatism means judging a thing by its practical effects on the world around us, not on their innate properties, their aesthetic, their beauty, does it make a change in the real world or not? And you can imagine that Peirce, in turn, is appealing to the work of a much earlier pragmatic philosopher. And what Master Yoda would have meant here by "there is no good, there is only good for," reasonable summary of Peirce's pragmatic maxim, is, we're engineers, we're supposed to be pragmatic. We need to be willing to look past our own aesthetic and principled beliefs about what constitutes good or bad practices in software, good or bad code, and judge things on the basis of whether they work in the real world. So we should judge the good of something not based on its intrinsic properties, but on what it is good for. So in that light, what do we think of this move fast and break things strategy? Well, as I guess it should surprise nobody at this point, I say both good and bad are the wrong answers. The answer is, of course, it depends. What's the situation? Is it right for the situation? And this leads me into the main subject of my talk today, which is engineering at the bottom of the stack, and how that differs from what a lot of us are used to. And one reason why this may be relevant, to all of you, and not just, a small subset, is that as our careers progress, we tend to move down the stack. And that's not because we choose to move downwards, but because the stack grows above us, and we generally stay in our comfort zone. And so relatively, what was the middle of the stack yesterday is closer to the bottom of the stack today. Now, I searched around for some Java software stack diagrams, and so I found a few of those. And I don't want to belabor the point. This one I found internally. This is the Oracle middleware stack. And the important thing here is there's a lot of stuff up there, and it's all sitting on Java at the bottom, right? And here's another one. This is the Spring stack. And again, there's an awful lot of stuff up there, and there's Java right there at the bottom. Now, of course, it's not really the bottom. There's stuff below. There's stuff below that. There's there's the hardware. There's containers. There's virtualization. All of that. But it's the bottom post part that we, as software engineers, interact with most of the time. Now, when you're the platform that everything depends on, moving fast and breaking things is probably a pretty poorly suited approach. And down here, the term for breaking things is bug. And with millions of users, there's really no such thing as nobody's going to notice. So down here, you have to place a very high priority on stability and compatibility. Now, it's worth noting that there was a time in Java's history when it wasn't the bottom of the stack, or even part of the stack. And in those days, we did move fast and break things. There was an awful lot of churn in the language and JVM design, certainly leading up to the first release, and then again in the years after that release. But things have changed a lot in that time. So, hang on a second. All right, where'd my mouse go? I have a serious technical problem here. Oh, I know what happened. Excuse me here. The projector confused my laptop. Sorry about that, folks. Okay. Anyway, success. The success of the Java platform comes with a price, and that price was we're not able to move as fast and break things as we were at one time. Okay, now when we talk about not breaking things, of course, we don't want to break our users' code. But this aversion to breaking things doesn't end with the code. The people part matters too, and it matters a lot. So we don't want to break our users' code, but more importantly, we don't want to break our users' expectations. We don't want to break their confidence in the platform. We don't want to break their mental models of how things work or the value of the investments they've made in their technical skills. And you can think of each of these things as a form of people compatibility. And they, in addition to binary compatibility and source compatibility and all the other sorts of technical compatibility that we worry about, people compatibility also places constraints on how we might evolve the platform. So as architect for the Java language and for the libraries, my job is to shape the developer's view of what Java is, which is the user-visible programming model. And of course, there's no shortage of, let's call them helpful suggestions that I get from developers all the time. But I find there's a big disconnect between what people think we do and what we actually do. So I made some fun little charts to illustrate the differences here. So this is one possible view of what an industry-focused language designer might do as viewed through the eyes of our academic colleagues. So in this view of the world, going clockwise from 12, clearly there's a bunch of time spent in meetings. And then the technical part of my job is mostly about the technical aspects of language design, creating a more expressive type system, adding features that lets us express more kinds of programs safely, or making the intent of programs more clear. And these things are part of my job, but this view completely omits the human side of things. When doing a particular group of features, we're going to have a time and resource budget like any other business, but we also have what we call a complexity budget. A complex feature may allow you to express some interesting and valuable new programs, but it can also do a lot of damage, both directly and indirectly. Directly, it can cause damage through misuse, and indirectly, it can cause damage because complexity distracts the developer from the task they're actually trying to accomplish. So keeping it simple means that it can actually be used and used correctly by real developers. Even simple and otherwise sensible ideas, might be discarded on the basis of cultural constraints. People have been programming in Java for 20 years, and they have a pretty clear idea of what Java is. And of course, we want to be able to evolve what Java is, but on the other hand, we don't want to break their ideas of what Java, is. So, for example, in Scala, conflicts between members inherited from traits are resolved by linearizing the supertypes. Totally reasonable idea, perfectly sensible feature, except for the fact that Java developers have 20 years of experience that tell them the order in which supertypes appear in an extends clause shouldn't matter, and changing that out from under them would have been disruptive. So when we did default methods in Java 8, we looked at, should we resolve conflicts the way Scala does it? Because that seems to work in that community, and we decided that was a sensible technical decision that didn't make sense for Java developers, and so we didn't do it that way. And these are considerations that someone coming from an academic programming language background would never think about. But when you're evolving a platform that's used by millions of people, it's really important. So this next chart is a little bit less charitable, so it's a little bit more fun. This is what I sometimes think folks in the community imagine I do based on what they say. So going clockwise from the top, you've got your secret backroom meetings and your conspiracies, and every once in a while, you poke your head out of the secret back room, and maybe, you make some obnoxious comments on mailing lists, and you come to a conference, and you do some self-promotion, and all of that. And then from a technical perspective, it's mostly about stealing features from other languages, and of course, the most important topic is syntax, right? That's what programming language design is. So, and it's fun to complain about this, and it's fun to vent about how people don't understand what I do, and it's certainly a little bit therapeutic. But it's also important to remember these are the people that we're doing it for. So in some sense, what success looks like is not correcting these misconceptions about how it works, but just make it better, right? Make it better anyway. James Gosling described Java as a blue-collar language. It's a tool for working programmers to get their job done. It's not an ivory tower creation. And there may be lots of rocket science in designing or implementing it, and certainly in specifying it, but you shouldn't have to be a rocket scientist to use it. And, of course, we have a pretty broad range of users in the Java community, and we can't afford to alienate any of them, because if we say, okay, we're only going to focus on the middle, we can lose sight of where the mainstream is headed. So, while Java may primarily have its home today in server-side business logic, we can't afford to alienate the more cutting-edge users like the high-frequency trading crowd, because that may be where the platform is going tomorrow. Okay, so this last slide is a little bit closer to reality. It has, some structural similarities with the previous chart. There's definitely a slice, for meetings and interacting with the community, but the technical focus of this one is different. It's not so much about adding features as it is about keeping features out. And if you look at some languages, you might think that the goal is to add every feature possible. And certainly, if you listen to users, what you get is requests for features. Please add this to Java. Please add that to Java. Relatively few requests to not add something to Java, which is where actually all the hard work is deciding what not to add. And in reality, adding language features should probably be your last resort, because every feature adds some bad weight. Every feature may interact with not only every feature that already exists, but every feature that you're going to add in the future. And that means that adding a feature today may foreclose on adding a much better feature tomorrow. So we have to choose our features very carefully. We're going to be living with them for a long time. We don't take features away from the programming language. We really can't, because there's so much code out there that depends on how the language has worked for the last 20 years. So a perfect example of the kind of feature that we end up living with for a lot longer than we'd like is my favorite, serialization. Right? You've probably heard me rant about serialization before. I could rant about it for probably the whole hour. But the point I want to make right now is serialization interacts with every single feature in the language. Every feature we've added has had some interaction with serialization. For example, like in the process of adding Lambda Expressions in Java 8. The interaction with serialization took up literally hundreds of hours of analysis and discussion. And that's actually a lot of time I'd like to have back to work on something else. So the remaining slices here mostly deal with the consequences of how features interact with each other in a language. And a common misperception about language features is that the hard part is either in the idea or the implementation and the compiler. And of course, ideas are important and implementations are important, but for the most part, in some sense, these are like the first 0% of the work. Because the real work comes from fitting them in with existing features, analyzing and testing for interactions with other features, and not just with existing features, but with all the other possible features that might be on our whiteboard somewhere. And this involves analyzing the compatibility consequences of everything. Now, the really fun part of what I do, which I get to do every once in a while, is this little slice here at the bottom, which is what would James do? Meditating on the true spirit of Java. I get to do that once in a while. It's pretty cool. Okay, so let's come back to our theme of don't break anything. The biggest slice on the previous slide was compatibility, and compatibility has many forms. And we worry about all of them. Now, the most important one that we worry about is binary compatibility. This is about whether existing class files continue to work, whether the call sites that are embedded in class files, which are dynamically linked at runtime, continue to link when I change other classes. Now, remember, everything about Java is dynamically linked. All method invocations and field accesses are dynamically linked by name at runtime. So when class A calls a method in class B, the signature of whatever method you selected is like in A's class file, and that signature needs to be present at runtime. Now, dynamic linkage is one of Java's secret weapons. This is what enables you to just drop a new jar in your class path and have everything continue to work. But dynamic linkage is a really strong constraint, because class files compiled in 1995 should still run today and should still run in 20 years. And if we're going to change the way that we compile Java to bytecode, we have to be mindful not only of having a consistent translation, but one that's consistent with all the class files that are out there now. So there's other forms of compatibility that we worry about. Source compatibility is whether clients or subclasses will continue to recompile after you make a change to a superclass or to a library. And behavioral compatibility means things continue to work the same way after a change. Serialization compatibility is whether instances serialized on an older or maybe even a newer version will deserialize properly. And there's a whole host of more subtle compatibility issues, like changes in performance characteristics or memory representation or footprint. And what makes this really hard is this cross-cutting concerns that runs through all of them, which is separate compilation. Because of dynamic linkage, you always have to deal with the possibility that only part of your system has been recompiled. And normally, this isn't a problem if you follow some reasonable rules for evolving your code, but separate compilation issues can really rear their heads up when you change something like your code generation strategy, or when the generated code for a given class depends on information from other classes. And this shows up with bridge methods, for example. And it's happened more than once that an otherwise perfectly sensible and worthwhile feature will get dropped because we can't do it compatibly. Now, this is not to say that we would never violate compatibility in any situation, right? You can't even fix a bug without breaking behavioral compatibility. But sometimes there are bugs we don't fix for this reason. So if we're going to do something that's an incompatible change, we're going to think about it long and hard and consider whether it's the right thing to do and whether the cost of some amount of breakage is worth the benefit of the new feature. It's not something we do lightly. Now, a lot of people think we're crazy to be this concerned about compatibility, right? But from our perspective, there really isn't any other responsible choice. When there's billions of lines of code out there, nearly any compatible change is going to break someone's mission-critical code. So it takes a certain kind of arrogance to say, yeah, you should break his code because it's for his own good. Has anybody ever heard that? I hear that a lot. We do get these suggestions, and I'm sure they think they're being helpful rather than arrogant because they're focusing on progress and not on breaking things. But their mistake is that they're only focusing on part of the picture, because what I see is that developers tend to overestimate the importance of their code, and they tend to underestimate the importance of stable programs. And this isn't surprising, right? Developers stare at code all day. So that's the part of the picture they see. But it's a little bit like one of those optical illusions, where depending on what part of the picture you look at, you see a different answer. Get it? Good, evil, good, evil. Everyone got it? Okay. So when users look at a language feature, what they're thinking is, what kind of code could I write with this feature? When we look at a language feature, we think about, not only what might it enable and how it might be used, but how might it be misused, how it might interact with other features, how it might change the style in which developers program, how migration of existing code to the new feature might cause subtle changes, and whether those changes are good overall or bad for the ecosystem. So our view of the world is not just it's about your code, it's about everybody's code. So at this point, you might be getting a little bit depressed. It probably seems hard to make any progress at all if you can't change anything, and that the sensible strategy might be just do nothing. And that is a guaranteed path to compatibility, right? Just don't ever change anything. It's also a guaranteed path to slow irrelevance. Evolving things compatibly isn't impossible. It's just harder. It's like working in any other difficult environment. You just have to approach the situation with the proper precautions and training and safety equipment, right? And if any of you saw my talk yesterday at the VM Technology Summit, it was all about how do you engineer under compatibility. We went through 3 different iterations of a prototype, each one moving the ball forward a little bit and addressing a compatibility issue of the previous. It's not impossible, it's just slower. Okay, so since it's not acceptable to change the meaning of an existing program, a language designer's next best trick is to expand the range of valid programs, to assign meaning to programs that previously would have been rejected by the compiler. So ideally, when you add a feature, you'd like to do it in a way so that it abstracts over the existing features. What I mean is, instead of adding a completely new feature, instead extend an existing feature to a broader range of situations. This is nice because it builds on users' existing mental models about how things work. And it's also less likely to create strange, new interactions. So the hard part is coming up with a sensible story, a sensible set of semantics for the existing feature so that when restricted to the conditions where it's currently valid, they match up, but they continue to make sense on the broader domain. So let me run through a quick example of this. In Java 8, we added default methods. And if we were starting from scratch and our goal was to support multiple inheritance of behavior, the rules for resolving conflicts between declarations of the same method in multiple supertypes would probably have been different from what we came up with. But to summarize briefly, before Java 8, interfaces could only contribute type information. They couldn't contribute behavior. So, you had an interface I. It said, to be an I, you have to have method M. We have a class C here that has method M but doesn't implement I. And then later you extend D, D extends C, implements I, and magically the method in C and the method in I become the same method, right? So this is how interfaces worked in Java before Java 8. Now in Java 8, we enhanced them to be able to contribute not only type information and members, but also behavior. So, in this old model, when D inherits M with identical signatures, both from C and I, it says, that's fine. We're just going to treat it as two different declarations of the same member. One of them has an implementation. One of them is just an interface declaration. It's all good. In Java 8, we allowed you to add behavior to the interface as well. So now, what happens with D? Well, D sees two supertypes that are both trying to contribute the same behavior, and ordinarily this would be a conflict. Now, we mark this behavior in the interface with this keyword that says this is a default implementation, and the default means if you don't have one, use this one, but if you have one, just ignore me. Okay? And this is how we got compatibility out of it. Right? We wanted to be able to add a default implementation to an existing interface method. We wanted that to be a source and binary compatible change. And so we ended up with an inheritance model that says what you inherit, behavior inherited from classes takes priority over behavior inherited from interfaces. Now, if we were designing Java from scratch, would we have done it this way? Probably not. We probably would have ended up with something more like traits. But that's not how Java works. We can't roll the clock back and say, let's redesign Java as of 1995. And so we found a way to extend an existing metaphor that developers were familiar with in a way that allowed us to express these new programs. And this way, we get a new feature, but we also get compatibility with existing code and with existing models about how dispatch works in Java. Right? So we call this philosophy embrace and extend. And this is a pretty standard language evolution trick. You adjust the rules to give priority to the old way so that any code that used to work continues to work exactly the same way. When we resolve a multiple inheritance conflict, we have three simple rules. First, if there's a conflict between a superclass and a superinterface, the superclass wins. And we don't even consider looking at the interfaces. And this is what gives us absolute compatibility with existing code. If it worked before, it's going to work exactly the same way, no matter how many defaults you add. And the second rule is if there's a conflict between two interfaces and one's a subtype of the other, the more specific type wins. That's really easy. And the third rule is there's no rule 3. If any other kind of conflict, that gets resolved by the programmer. And this was a choice we made towards simplicity of rather than trying to read the programmer's mind and guess what they wanted, we just said, if you're in this situation, you decide what you want to do here. So this kind of thinking is what I meant earlier by adjusting a feature to fit in with other features. The rules we arrived at, which is that implementations and interfaces are just defaults, and they're subordinate to implementations and classes. This wouldn't have been what we chose, probably, if we had been inventing an object-oriented language with multiple inheritance of behavior from scratch. But that's okay. There's more than one sensible way to design a programming language. This is a perfectly sensible and understandable model, and this is compatible with what we had before. And we've used this trick over and over again. You probably haven't even noticed. When we added autoboxing in Java 5, which was an implicit type conversion from int to integer, if we had done this naively, this would have changed some existing method overload selection decisions because it changed the set of methods that are applicable at a given call site. So in order to prevent this from changing the semantics of existing code, we created a set of tiered rules for overload resolution, where the first step is basically the old rules, and the later steps only come into play when the old rules don't give an answer. So we call this strategy embrace and extend because you embrace the existing semantics first, and then you find a sensible generalization so that it that both stands on its own and matches the existing semantics. This is one of our best tricks in evolving the language, but you have to use it carefully, because if if each change involves adding something to the rule set, step 1, do the old thing, step 2, do the new thing, you don't want to let that list get too big. Complexity can get out of hand, so you have to use it judiciously. So, the previous example with default methods and the one with overload selection worked out pretty well, and we're pretty happy with the results. And, but these ideas don't spring fully formed from day one. In fact, it took between 2 and 3 years from the time we cooked up the crazy idea of, what if we could attach behavior to interface methods, and we actually arrived at a sensible model that Java developers didn't look at and say, what is this alien contraption nailed onto the side of my language? And, well, some people are going to say that no matter what you do. But certainly, you want, when users see a new feature, you want them to think, oh, I know what that means, rather than, oh my God, what is that? Did I open the wrong file? So, as we often do, we go through multiple iterations of the design process. And each iteration seemed an improvement over the previous one. But it probably wasn't until we got to like the 6th iteration or so that we get something down to something simple enough that the rules can fit on one slide, like the rules I just showed you in the previous slide. But there's a real danger here to watch out for, and that is, since each iteration is simpler than the previous one, at almost any point we could have made the mistake of convincing ourselves that we're done. Look how much better it is than it was last week. And it often takes a lot of time and a lot of iterations to find the right idea. So more than once, I've had to tell my management that we're not there yet. We're not ready to ship, and it was going to take longer than maybe we'd hoped it was going to take. And thankfully, due to supportive management, the answer has always been, take the time and get it right. Because when you're contemplating something you're going to have to support for 20 years, and which is going to further constrain what you're able to do next year and the year after and the year after that, you need to be able to take the time to do it right or not do it at all. So I recently came across this quote from Steve Jobs, which perfectly echoed the experience we had with evolving Java in Java 8. So he says, when you start looking at a problem, and it seems really simple, and you have all these simple solutions, that means you don't really understand the complexity of the problem. And your solutions are way oversimplified, and they don't work. And then you get into the problem, and you see, wow, it's really complicated. And you come up with all of these complicated solutions. And this is the middle. And that's where most people stop. And the solutions that you come up with at this point, they tend to work for a while, but the really great person will keep on going until they find the key underlying principle of the problem and come up with a beautiful, elegant solution that works. So, the really hard part is when you found something that works, realizing I'm still in the middle. And having some faith that there's a better answer lurking in there, even if you have no idea what it is. And it's incredibly tempting to just declare victory and stop there and ship it. Look, we did this. It works. It's great. And, the complexity of the problem actually works against you because you're thinking, well, I know this problem is complex, so the solution has to be complex. And you think you're not going to find a simpler solution. And then you may be dealing with external forces saying, but it works, why can't you ship it? So, an even more extreme example of this, give it as much time as it needs principle was generics themselves. So last year, or a year and a half ago at Java 1, James Gosling told this story about why generics weren't included in the first version of Java. And it's not because in 1995 we didn't understand parametric polymorphism. It's not because we didn't think it was a good idea to have a static type system that was so weak that when you put things into a collection, they can't retain their types when they come out. It's because we didn't know how to do it right. And there was some temptation to push forward anyway. And the solution we would have gotten in 1995 would have been more like C++ templates or maybe patterns from Beta. And I think we're all pretty glad we didn't get that in Java 1.0. And certainly it took longer than we liked. I mean, it took 10 years for generics to come into the language. But the generics we got were much closer to the spirit of the language than what we would have gotten in 1995. So if you don't know the right thing to do, at the very least, don't do the wrong thing. Sometimes that means doing nothing, and that has to be okay. Another way to sort of state this is reality hardens like concrete. Before you do anything, there's all these paths ahead. It's all potential. Once you do something, there's many fewer paths ahead. Maybe there's only one. And this is true for little things as well as big things. So you should always try to be aware of not only of what doors am I opening, but what doors am I implicitly closing with my choices. So a related aspect of this is beware and be skeptical of the inclination to punt on the hard cases. When you've gotten 80% of the way through a problem and you think, oh, this is good enough, it's really tempting to say, the last little bit, that's not that important. When you start thinking that way, that's a sign that you're still in the middle. And the reason this sense of finishing the job is so important in language design is that what might seem like a clever compromise today is tomorrow's incomprehensible irregularity. And it's often tempting to give in to solving the easy cases and punting on the hard ones on the theory that, well, we've at least moved the ball forward, right? Something good has happened. But developers are really allergic to irregularities in programming languages, for good reasons, because irregularity breeds complexity. And the complexity distracts them from the programming task at hand. So, naive suggestions like, well, we'll just make a language restriction that you can't do X when Y happens. And we get these suggestions all the time when we're in the process of developing new features. It may seem like a practical shortcut, but they're going to be tomorrow's, what could they have been thinking questions. All right, so the next bit of advice might feel a little bit like the opposite of the previous one, which advises against accepting irregularities because building a regular solution is hard. But on the other hand, we also have to be skeptical of the motivation to do anything for reasons of consistency. Now, consistency is a reasonable guide, of course, and we'd rather be consistent than inconsistent. But we should really watch out for the desire for superficial consistency, because that tends to replace a deeper analysis of the problem. And in my experience, where I get hundreds or thousands of suggestions from users about what we should do in Java and why, the most poorly thought out suggestions all involve the phrase "for consistency." It's like a big red flag. Now, that doesn't mean consistency is a bad goal. I mean, consistency is a great goal. But you should be suspicious of using it to justify anything. The American philosopher Ralph Waldo Emerson said, in his essay Self-Reliance, a foolish consistency is the hobgoblin of little minds. It's often misquoted, though, and it leaves out the most important word, foolish. So we need to be vigilant to separate the sensible consistencies from the foolish ones. Okay, so most of you have probably programmed with Java 8 so far, right? How many people here have used Java 8 so far? All right, that's excellent. I love seeing this. So the things that I've said, up until now have been sort of like lessons learned from the Java 8 process. And Java 8 was a great upgrade, probably the biggest upgrade to the Java programming model ever. We had coordinated improvements in the language, the JVM, and the libraries. So what's next? How can we apply what we've learned to keep moving the platform forward? So our approach for picking evolution targets is a pragmatic one. We try to pick the largest pain point, hammer away at it, and iterate. So for Java 8, the big pain point was pretty much language-driven, specifically the inability to abstract over behavior. So we introduced Lambda Expressions that let you write libraries that abstract over behavior. And in Java 9, the big pain point is that of programming in the large, reducing the pain of assembling large applications out of components and using those techniques to modularize the platform itself as well as applications. But pain points are often hardware-driven as well. And we want Java and the JVM to continue to perform well on the target of moving hardware. And so in the versions of Java after 9, we're focusing on aligning Java's view of the hardware with how hardware has changed in the last 20 years. So How has hardware changed in the last 20 years? Well, the short answer is a lot. In the old days, we had single-core, single-socket systems with no cache, no instruction-level parallelism, and no pipelining. And in those days, a arithmetic operation cost about the same as a memory fetch. And the performance model was really simple, basically count instructions. And over time, our systems got more complicated. You started out just with core and memory, and we added caches, and we added multi-layer caches, and we added multiple cores, and we added multiple sockets, and our systems got bigger, and they got more sophisticated. And the cost of all of that was the cost of a memory access got less predictable. Cost of a memory access today ranges from a few cycles if your data is in L1, to a few hundred cycles if your data is all the way out in main memory. And at the same time, our cores got fancier. They have deeper pipelines, superscalar execution, and as a result, if a cache mess is going to cost you, let's say, 300 clock cycles, and we can issue 4 arithmetic operations per clock cycle, a cache mess might cost as much as 1,000 arithmetic operations. So that's like 1,000 to 1 change in the relative cost of 2 operations over 25 years. So it stands to reason that given these changes in the underlying cost model, whatever trade-offs we made in 1995 about how Java lays things out in memory couldn't possibly be optimal for today's systems unless we got really, really lucky, and we didn't. So if you think about the JVM type system, you've got your 8 primitive types, int, long, double, etc. You've got classes, you've got arrays. So this is simple, this is flexible, and you can model anything you want with it. The problem is the flexibility isn't quite in the right places. Primitives are more rigid than we'd like, right? If you want, unsigned, integers or 128-bit integers, and they don't fit into the existing primitives, you're out of luck. And on the other end of the spectrum, objects are actually more flexible than we need because all objects have identity. And object identity exists to support mutability and polymorphism. And not all objects need this, but all objects pay for it. Now, you might think that the VM's just going to figure this all out, right? JVMs have gotten really good at slicing through the cost of code abstraction, but they never really got very good at slicing through the cost of data abstraction. And the problem is, fundamentally, that the VM is not really able to figure out that when you allocate an object, that you're never going to do an identity-sensitive operation on it, because any object could be used by any code at any time as a lock or something like that. So the VM ends up being pessimistic about how it lays things out in memory. So to illustrate this, and I know not everybody is used to thinking about the hardware characteristics, which is a good thing, right? You should be thinking about the business problem you're trying to solve. But we're thinking about how do we make it so that the obvious code is also the fast code. So for our illustration, imagine you've got a simple data class like an XY point. And let's say you're following good practices, so your class is immutable and final, so it's not going to be polymorphic. It really has no need for an object identity. But like I said, whether you want it or not, you get it, right? Everything comes with fries. So, if you have an array of these things, well, an array is an object. It has an object header. And each of the points in this array is going to have a pointer to another object with an object header. And these are allocated dynamically, so who knows where they're laid out in memory. And if you think about this from a memory efficiency perspective, how well are we doing? We have 2 words of data for each point, and for each of those we have 2 words of header and another word of pointer. So that's like 150% overhead. 60% of your memory is lost to overhead rather than data. So that's not so great. But even worse, these objects are heap allocated, so we have to follow a pointer, to get to them, and that's of course work also for the allocator and the garbage collector. But the real cost comes from the arrows, the pointers, because it means, if you're every time you want to get one of those, get your XY point data, you have to follow an indirection, and that's a potential cache miss. If you have like an array of just plain old integers, just an array of ints. You get great locality when you're accessing the data. When you access the first one, it's going to pull like the next 15 into cache along with it. And then by the time you've looked at the second one and the third one, the prefetcher has already kicked in, and it's pulled the next 16 into cache. So you get really nice locality, really nice memory access behavior, and you get to spend most of your time computing and not waiting for data. If you have an object graph like this one, you're going to spend most of your time waiting for data. Every time you traverse one of those pointers, you're probably going to cache miss. And cache misses can be expensive. And maybe this is fine. Maybe you don't have a lot of data. Maybe your performance requirements are modest, and you're just focused on getting the right answer to your problem, and it's not an issue. But if you're doing something like high-frequency trading or big data analytics, this cost really can count for a lot. And you didn't ask for this layout, right? What you'd really rather have is this layout, right? Now, when confronted with a situation like this, developers often take matter into their own hands, and sometimes they have to, and sometimes they just can't help themselves. But they'll often do ugly tricks like this, like they'll shred the array into two separate arrays, an array of x's and arrays of y's, hoping to regain the locality that they lost to the object layout. And how many people here have done stuff like this, right? I do it too, but it's regrettable. You don't want to do this. This is wasted time, this is wasted effort, and this code is harder to write, it's harder to read, it's easier to make mistakes. And the really sad part is some people do things like this, for performance reasons, with no actual evidence that their code isn't already fast enough or even without any performance measurements or goals at all. But regardless of whether developers do this out of a genuine need or out of some destructive obsessive compulsive disorder, the winning move for us is to stop putting developers in the situation where they feel they have to choose between writing good code with abstraction and encapsulation and getting good performance. We'd like to be able to write good code and just get good performance out of it so people don't do stuff like this. Which brings me to a feature for today's hardware, value types. So if we recast our point as a value, what we're saying is we don't care about the identity. We don't care about what that brings with it. We're willing to give up a little bit of flexibility to get some benefit. So this allows us to treat an aggregate like an XY point as a value. Now, values like ints and longs, they're implicitly immutable and final. You can't change what 3 means, right? And they derive their equality from state rather than object identity, and they get passed around by value in registers or on the stack rather than on the heap. So this means that we can flatten their state into arrays without additional indirections, and we can also flatten them right into objects. And values can have most of the things classes have: methods, constructors, fields. Their methods can be public or private. They can be generic. And because values are not polymorphic, there's no dispatch cost for invoking their methods. They act just like static methods. And so the mantra here is, codes like a class behaves like an int. And the applications for this are obvious, right? Better numerics, unsigned int, 128-bit int, complex, tuples, algebraic data type like optional or choice, cursors like you see in the C++ standard template library. And the cool thing is, even though there's no expressiveness improvement here, because it doesn't give you anything you can't do today with objects, it lets you do them without worrying about the cost. And that's great because as developers, we often worry about cost even when we shouldn't, because we're wired to do that. So by making the right thing and the fast thing the same thing, we remove a whole source of friction from the development process. And because value types have encapsulation just like reference classes, we can use them to be like secure, cost-free wrappers around sensitive data without paying anything for it. So it's like a free lunch, right? Safety, maintainability, and performance. Who could object to that? So if you look at generics, if you have generics and using box primitives, like if you have an array of array list of integers, you end up with the same looking memory layout as I had in the previous slide, and all the same costs. Inefficient use of memory, too much indirection, not enough locality, too much allocation and garbage collection. And from a language perspective, we're talking about how features interact. Once we add value types, you immediately see that the compromise we made in 2004, which is you can generify over references but not primitives, this really starts to fall apart, right? If we have these new kinds of programmable primitives and we couldn't generify over them, well, that would be terrible. So we're going to have to finally bite the bullet and support generics over primitives and over values so that you can say array list of int and have it backed by a real int array. and the VM takes care of the specialization. And this is what my talk at the VM Summit was yesterday. So if you're interested in this, go check out the video. So these two features that I was just talking about, value types and generics over primitives and values, are part of a bigger effort to reboot the JVM's relationship with memory and to balance the need for abstraction and encapsulation with the performance realities of modern hardware. But this is pretty cool, right? This is like teaching an old dog new tricks. So, all right, so let me wrap up. I'll close with a warning, which is be careful what you wish for. We all want the software we write to be successful and used for many years by many people. And success brings with it some costs and constraints that can be a little bit frustrating at times. On the other hand, these constraints, most notably keeping the promises you've made to your users, whether you've made them explicitly or implicitly, forces you to spend a lot more time up front thinking about whether something is the right thing to do and what the possible consequences might be. And most of the time, thinking deeply about what you're going to do pays off, even though it means you can't rush forward as quickly or as as flexibly as you might otherwise want to. So, thank you for listening. Enjoy the conference, and don't break anything on the way out.